We have the mobile phase, which is your gas. And like I said, we'll look at the critical issues surrounding the mobile phase. But one key thing we need to know about the mobile phase is that it must be inert because it should not interact or react with your analyte or your sample that you are interested, you're working with. And your gas cylinder is as a regulator that enables you to know when you are running out of gas, because it's not a transparent container that you know when your gas is finished. And you don't want to be running your analysis and gas gets finished, just like you're cooking and your gas cylinder gets empty while you're cooking. But when you are doing this, you want it to be sufficient to start the analysis and to complete. So you have a regulator here. The regulator does two things. It regulates the tells you the content, the volume of the gas, and also the flow rate, because you have to also regulate the flow rate. We'll look in depth. If somebody is asking for the type of gas, we'll look at that later on. But the carrier gas, we have the carrier gas, we have the makeup gas, we have also what we call the detector gases. Some gases also make use of detectors, as well as your instrument needs the carrier gas to move your sample. We have what we call the traps here. You want your gas to be pure, at least 99.9%. So this trap here would trap, it will be like a trap for moisture. If there's moisture in your gas, it could be a contaminant into your column. And also, if there's any impurity in your gas, that impurity also can be detected in the column, can be separated in the column, gets detected, and you have a chromatogram for it. So you want your gas to be at least 99.99% pure. So the trap here will trap everything that is a contaminant or impurity in the gas. Then we also have the sampler. This is where the sample is introduced into the chromatograph. So the sample is introduced there through the inlet. So there is a syringe here, like a barrel of a syringe, where your sample is taken in and it gets introduced into the column. The column sits in an oven. So this is a stationary phase that is coiled. Remember, I told you that a GC can have a column as long as 100 meters. Though the most common columns are about 30 meters, 60 meters, but we have those that can be as long as 100 meters. And you know how long 100 meters is. So it has to be wound in a coil and it sits in an oven. Also attached to your oven is the detector. So the detector, your analyte, when your sample gets in, it travels down the column through the entire length of the column and it gets into the detector. So you have your detector here that picks the signal as different analytes arrive at the entry of the detector. A signal will be sent via the computer and you have what we call the chromatogram. So this is the schematic diagram of your gas chromatograph. So what's the principle of operation? The sample is injected using a syringe into the injection port. Remember, we mentioned the injection port. So a syringe is there that introduces the sample into the injection port. And because your injection port, your inlet, is also sitting in an oven, so it is a heated environment in the gas chromatograph. So the sample would now vaporize in the injector and it is forced into the column by the carrier gas, which is your mobile phase. And the most common gas used in the mobile as a mobile phase is helium. We are going to look in depth at different types of gases. So let's say we are using helium. So your sample is vaporized and it passes through the column and the carrier gas, meaning that before your sample is introduced, the gas would have been flowing. So ever before your sample is injected into the GC, when you put on your instrument, your gas begins to flow. So the injection of your sample is into the stream of the mobile phase. And so as it's injected into that stream, the mobile phase automatically carries it into the column. So the components of the sample mixture will interact with the stationary phase in your column, and different analytes will interact differently with the stationary phase. So different analytes will take different amounts of time to elute from the column. We call that process elution. So the process of your analytes getting out of the end of the column is called elution. So different components in your sample would elute at different times. And the time they come out of the column will be reflected in the chromatogram by their different retention times. We looked at that in the previous class. So the separated components, when they get to the end of the column, will be passed through a detector, which takes note of which analyte arrives and what time and what quantity of the analyte arrives at the detector end. So the detector has electronic signals that will be sent to the via the to the GC software. So there's a software on the computer that controls the entire system. So this computer here will be the one that we can set the flow rate of the gas from the computer. You can set the temperature of the oven by the computer, the temperature of the detector, the temperature of the inlet, even the volume of your sample that you want to get into it. So the computer is like the brain that controls the entire system and also coordinates whatever signal that the detector picks and the chromatogram is generated. So that is the simple principle of GC. So in exam, if you're asked to tell us, you don't have to tell a story beyond this. The sample is injected using a syringe into the injection port. The sample is vaporized and it is forced into the column by the carrier gas, which is your mobile phase. And the components of your sample, which are your analytes, interact with the stationary phase in the column, and they elute at different times from the column. And as each analyte elutes from the column, the separated components pass through the detector and the signal is generated and your sample elutes from the column and the chromatogram is generated. So now let's look at these key components. Like remember the 5 components that are the key components are the mobile phase, which is your carrier gas, the inlet, the oven, the column, and the detector. So let's look at them one after the other. The first stage is the gas supply unit. So this is your GC. This is a picture of a GC. I can see beside the GC are your cylinders. So this is a GC machine. It's a tabletop instrument coupled with your gas cylinders. So the gas cylinder supplies all the necessary gas that is needed for the mobile phase. Sometimes some detectors also make use of gases. And that is why instead of you, like in the schematic diagram here, we have just one gas cylinder. But the one we have in the department is exactly this. It is coupled with 3 different cylinders. So you might be wondering, is it using 3 mobile phases? No. In this particular case, for example, one of the cylinder is the mobile phase actually, while the other 2 are the gas supply for the detector. And an example of that is the FID. It is called flame ionization detector. The FID requires 3 different gases, and I'll name them one after the other. We have your mobile phase, which is nitrogen gas. Then because the detector is a flame, there's a fire inside this detector, and it also needs fuel. And the 2 fuel it uses are air and oxygen. It uses air and it uses the oxygen gas, which serves as the fuel for the detector. So that is why for this particular GC, you will see 3 different cylinders. But for other types of detectors, because we have different types of detectors, you will only see, once you see just 1 cylinder, you know that that GC is not using a flame ionization detector. The only gas there is the mobile phase. But when you see 3 cylinders, that means that the other 2 gases are hydrogen gas and your air and hydrogen. Sorry, hydrogen and air are the 2 gases that the flame that generates flame for the flame ionization detector. So then there'll be a microprocessor in your computer. There's a computer coupled to this system that will monitor the flow rates of these different gases. So there's a microprocessor that does that. But sometimes you get to a place where the cylinder, you won't see any bottle of cylinder close by. We have what we call gas generators. I see them on the slide here, gas generators. So your nitrogen can be generated from the air. Atmospheric air can generate nitrogen. And also oxygen, hydrogen can also be generated from water. So you can get water that will generate hydrogen, and your air also can be generated from the atmospheric air. So sometimes you make use of gas generators, like the one we have in the department is coupled to gas generators, because a cylinder, for example, of nitrogen is over 100,000 naira. But if you buy a gas generator, there are some gas generators that maybe for a million naira, you buy a gas generator. And thankfully, we are not buying air from God. God supplies air freely. So the gas generator will just generate the nitrogen gas, and your GC continues to work without. So sometimes you won't see cylinders there. You see what we call gas generators. And for health and safety, some laboratories will not put the gas cylinders directly beside the GC. They put them outside. So the pipes will come in from maybe from through the window and get connected to the machine. So it's not all the time the cylinders sit close. You can sit close to it, or you put them outside, like in the Central Research Lab, the DK Olukoya lab. The GC there is not inside the laboratory, but outside. And the pipe brings in the gas into the machine. And this is the flow monitor that we have. And like I said, the flow monitor is connected to the cylinder. You can see the gauges on top of the cylinders. One of them tells us the content when the cylinder is getting empty, it tells you, and also lets you to know the flow rate of the gas. So there's a knob that is fair. The gas cylinders is fitted with monitors. Then we have the injector. The injector, if you go back to the schematic diagram, you have that is the inlet where your sample is introduced into the machine. So the injector can be manual or automatic. So we have two different types of injector. We have the manual injector and you have the automatic injector. So the injector is the place whereby your sample is introduced. You can see the manual one. The operator is manually holding the syringe and is plunging the syringe right into the injector. That is manual. We have the automatic injector whereby you can have a carousel and your sample vials are loaded on the carousel. So there's a robot that will pick up the vial that you want to inject, and it will inject it automatically into the machine. Like the one we have in the department, it has both the manual and the automatic injector. So you don't have to sit down there. So you can load some carousels can have up to 100 trays. And in a place where there is no power supply, I remember then when I was doing my PhD, I put all my samples on the machine. Over the weekend, I just go and because light is always constant. And when I come by Monday, all my samples would have been by itself. It will pick it up, inject into the machine. And when that one is finished, you go again, pick another one, inject into the machine. And so you don't have to sit down there. You can do some other things and your data will be stored into the computer. So that's the automatic injector. And like I said, because you want to introduce a sample as a vapor, the injector must be hot. So the injector is also situated in a thermostatically controlled enclosure, usually an oven. You can see the manual injector. The injector is enclosed here, which is a heated zone. So the sample, as the sample is injected, it forms vapor, and the plug of vapor automatically goes into the column. So the automatic injector is on a carousel, and you can carry out series of sample preparation procedures before you inject the sample into the column. So like for example, if I want to analyze my soil sample or water sample, it's not the water sample that will be here. it will be the extracts. Maybe I've used liquid extraction, or I use Soxhlet extraction, or SP, whichever method of extraction. My sample would have undergone sample preparation procedures prior to getting to this stage. So the analysis stage is the simplest. Sometimes there are some samples that you work with that your sample preparation procedure can take days, but the injection will just take a minute. So, and you know that it's garbage in, garbage out. So if you don't do good sample preparation procedure, you will be introducing a bad sample into the machine. So no matter how sophisticated your GC is, if the key thing is that your sample preparation procedure must be top notch, such that you introduce good samples and you inject it into the column where the separation will take place. Then the next major part is the oven, and your oven is where your stationary phase sits. So your column is your stationary phase, sits in an oven. Your column sits in an oven, and for any separation to take place in GC, column is the key major factor, because your column is where the separation will take place, and your column is housed or in an oven. So inside the oven, you have your column. So your column would have two ends. Let's go back to the schematic diagram. So this is your column sitting in an oven. There are two ends. One end of the column is the inlet, which goes into the injector, and the second end of the column is the one that goes into the detector. So as the column sits in an oven, one of them goes here into the injector, and the other end goes into the detector. And your oven can be top loading oven or side opening oven, just like you have your washing machine. You have a top loader washing machine that you open from the top or you open from the side. So your oven also can be configured in that way. They can be side loading or top loading oven. And the oven also is what controls the temperature of the column. So your column must be hot, and the oven is what will give the right temperature, and it is in a thermostatically enclosure, meaning that once you set a temperature, that temperature is fixed. It can't be altered. It can't go lower or go higher. So look at the GC as a GC machine as it is. So this is a GC cylinder. You have your computer. Remember, we said that it's the computer that controls what goes on in this GC. So this is the auto sampler. Your auto sampler is what brings in your sample into the injector. Then you have the oven. This is a side loading oven. So this can be opened like a door, and your column is there, and your detector is just by the side. You can see your cylinder here and your gas. So you can control the flow of the gas either here or on the column, and you see the detector by its side. So this is a gas chromatograph with an auto sampler. So now the detector is enclosed also in the oven. You can see the detector here is beside. There's an oven. There's a temperature for the detector as well. And depending on the analytes of interest, there is a wide range of detectors that are in operation. Each of the detector has its own characteristics. So we look at different types of detectors in the course of the lecture. And the output of the detector is electronically modified, as will be seen on the computer. So in the GC, there are three distinct zones where temperature must be controlled and must be adjusted before a GC separation can take place. The first place is the injector. So the injector sits in on the oven, and the temperature must be controlled because you want your sample to immediately evaporate or vaporize as soon as it's injected. You don't want the sample to sit down there and form and condense there. And if the sample sits at the injector, it won't be carried easily by the mobile phase into the detector, into the column. So the injector is one temperature zone. The second temperature zone is the column. And when you are setting your temperature, the temperature of the injector is always higher than that of the column. So you increase the temperature of the injector above that of the column so that it will go vaporize and go flow into the column. And finally, the detector also should also be at a reasonably high temperature so that as your analytes are eluting from the column, they don't get condensated. There's no condensation of your analytes. So you want to analyze as it's coming out of the detector hot without condensation, goes into the detector and the signal is picked. So if you're asked in the exam, what are the 3 temperature zones in the GC? You have the injector, the temperature, the injector zone, the oven, the column, and the detector. So these are the temperature zones in the GC. So now let's look at the carrier gas supply. Talking about gases, somebody has asked the question in the chat room, asking that what are the types of gas that we use. So the type of gas that we use for gas chromatography must be chemically inert. You don't want a gas that, as the gas is carrying the analyte, it will also, the impurity there, it will be reacting and be changing the configuration or the property of your analyte. So your gas, your carrier gas, must be chemically inert. And examples of chemically inert gases that are used are helium, nitrogen, and hydrogen. Sometimes your carrier gas will be determined by the type of detector. For example, if you are looking at mass spectrometer as a detector, the type of carrier gas we use will be different from when you are using an electronic electron capture detector. So the type of detector will determine the type of carrier gas that you use for your mobile phase. Then associated with the carrier gas or the gas supply are the pressure regulators, the gauges, and the flow meters, which we have seen before. We have your regulator and the gauge and the flow meter. See here now that we have on the gas cylinder, you have your regulators and the gauge and the flow meter on the cylinder of your gas supply. Then also the carrier gas would have a trap which contains a molecular sieve to remove water or other impurities. You don't want moisture. Moisture can destroy your column. And one column of a GC is over ₦500,000 now. A column of a GC is about between 400,000 naira and 500,000. And you can imagine if you now allow water to get into that and it destroys your column. So to forestall any form of damage to your column, you have to put a sieve, a molecular sieve or a trap whereby moisture, water, or any other impurity in your gas will be trapped before the gas is allowed to flow into the GC. So the choice of the carrier gas can also be dependent, which I've said before, on the type of detector that you are using. A mass spectrometer detector will use a different gas from an FID or an ECD. And also, in addition to this, if you are using a flame ionization detector, you also need to get gas for the flame. And the gas we use are hydrogen and air. So those are the gases used when the detector varies. So gases, we've said before, can be nitrogen, helium, or hydrogen. And this puts a little limitation on gas chromatography. What do I mean by this limitation? Because the gases we are using are limited. We don't have a wide array of gases that we are using. So the mobile phase in gas chromatography is limited. Unlike in liquid chromatography, when we get to liquid chromatography, you can have up to 1,001 types of mobile phase. You can mix acetonitrile with water. You can mix water with acetone. You can use methanol. You can use tetrahydrofuran. You can use buffers. You can use water. So there are loads of gas mobile phase for liquid chromatography, and that would also help us in optimizing the efficiency of the separation. But for gas chromatography, the only thing we can play around here is the temperature of the oven, of the column. So we are limited in the type of gas that we use for gas chromatography. So that is one limitation. So even in an exam, you are asked, what is the limitation in using gas as a mobile phase? And that is that we have limitation in the variety of gases that can be used as our mobile phase. Unlike liquid chromatography, where you have a wide option, I can mix up to 3 or 4 solvents in different ratios, and I will get a different result. If I use 50% water, 50% methanol, the result I will get will be different from when I use 10% water, 90% methanol. So we can do a lot of modification with the mobile phase in liquid chromatography, but for gas chromatography, that is the limitation. So the properties of the gas, like I said before, it should be at least 99.99% pure. So even if you are using your gas generator, the gas generator should be able to generate very clean supply of gas. And I've said the reason why your gas must be pure. If your gas is not pure, if there's a contaminant in your gas, it can react with your analytes. So and your results will not be credible. And also, even when your gas is not pure, it can also damage your column. And I've told you the price of a column. If you're buying a column that should serve you like 2 years, within 1 month, a column of 400,000 naira is damaged. You can see that that is a very, very big risk. So you must use a very pure gas. And the gas should also be inert, as I said before, so that it will not react with your stationary phase or other components of your instruments, especially at high temperature. Remember, gas chromatography works with temperature. So if the gas is not inert, maybe at elevated temperature, it can deform or alter the nature of your analytes. Let's say maybe you are looking for naphthalene, and there is your gas reacts with naphthalene and it forms another, maybe oxynaphthalene. It has changed the nature of your sample. Then you want to also prefer a gas that has large viscosity and high density. And that is why we make use of helium or argon. Argon also has higher density than helium, but it's very expensive. And the gas should also have high diffusivity. You should be able to diffuse and be able to carry your analytes easily. So that is why you want a gas with higher density and larger viscosity. Then also your carrier gas must be compatible with the detector. So if you are using flame ionization detector, for example, you can't use helium as your gas. You have to use nitrogen as your gas. If you are using mass spectrometer, you have to use helium as your carrier gas and not nitrogen. So there must be compatibility between your detector and your carrier gas. And your gas should be available and must be cheap. And that is why nitrogen is cheaper than helium or argon. And nitrogen is a very popular carrier gas. And you can easily generate nitrogen from atmospheric air. You know, your air contains over 70% of nitrogen. So it's easy for us to generate nitrogen from atmospheric air and save the cost of refilling a cylinder at over 100,000 naira. Then your gas also should not cause risk of fire or explosion. So there must be safety put in place for your gas so that your gas will not, it should not be an easily combustible gas to avoid the risk of explosion. So your gas must be dry, pure, and must not react with the components of your sample, which I've said before. I'm just reiterating this. Your gas, the higher the purity of your gas, the lower the baseline. Remember I talked to you about the baseline. Talked about baseline before. You said a baseline in your chromatogram. If you have your chromatogram like this, your baseline, this is your, if nothing is coming out, it must be flat until your peak is found. So this is your baseline. So if you use a good your gas, your baseline will be flat. But if you use another gas, maybe your gas contains impurity, you have your baseline will be something like this. You have maybe a wavy waveline. This is your waveline before your analyte is seen, and your waveline will be like this. So you don't want this baseline to be wavy. So if your gas is very pure, when nothing is coming out, when there is no analyte, you see it very flat, smooth, and it will only come up when there is an analyte or a component, and it goes back again when nothing is detected. But when you use an impure gas, your baseline will not be pure. Your baseline will not be pure, and you now have a wavy baseline. So that is the reason why your baseline must be very your gas must be pure. And when it is pure, your baseline will be flattened, and your instrument will be very sensitive. You can imagine if there's an analyte that is supposed to come out here. Let's say you have an analyte of a very low concentration, and the peak is here. So your peak you can now see here now that if there is a chromatogram coming out, a peak at this particular place, if your baseline is very noisy and an analyte is coming out there, you won't be able to distinguish between your baseline and your components that is being separated. So that is the reason why your gas must be pure. So at the slightest thing that will come out there as a peak will be observed. If there's a chromatogram a peak coming out from here, it will be easily seen. But if your chromatogram is noisy, your analyte, your peak will be lost in the chromatogram. So also, your contaminants would interfere with, it can also be detected. So let's say you inject a clean sample, one component, one analyte. If your gas also has different contaminants, your detector will just be seeing 20 peaks. You'll now be like, I'm expecting just one chromatogram or one peak in my chromatogram. Why am I seeing 4 or 5? There was a time one of my students was looking at, was injecting a pure standard that had just 4 components. When she brought the chromatogram, we found out the chromatogram had about 6 peaks. I was like, are you sure you injected pure standard? She said it was pure. Later on, we found out that the solvent that she used for extraction was not pure. So by the time we injected the pure solvent, we found peaks, 2 peaks in the solvent. So meaning that the detector can detect anything that gets there. So that is why you have to be careful that you are not introducing contaminants into your carrier gas, so that if the contaminant is in the gas and it passes through into the column, the detector would also detect it. Then we've said before that GC columns can be damaged by moisture, by oxygen, by water, or other contaminants. And also, contaminants not visible with all detectors can hinder the quantification or damage the column. So there are some contaminants that may not be detected, but there will be a damage to your column, and you don't want your column that is expensive to get damaged within a short period of time. So now the next, after leaving the gas system, we go to the sample introduction system. And this is another critical aspect of the GC, because one thing about GC is that you are only introducing very, very, very little quantity of your sample. Some GC, you only introduce 0.1 microliter. Can imagine 0.1 microliter of sample. And if that 0.1 microliter that is 1,000 ratio of 1 mil, 1/1,000 of 1 mil. 1 into 1,000 parts of 1 mil of a sample. You can imagine how little 1 mil is, and you are taking 1,000 fraction of 1 milliliter. That is how small 0.1 microliter is. So you have to be sure that you don't lose, because if that thing is lost, you will not see anything in your chromatogram, and your results are not detected. And in actual fact, nothing got into your detector because you did not introduce it well. So the introduction must be in such a way that your sample is introduced into the system and it must vaporize instantaneously. And that's the reason why I said your inlet, where your sample is introduced, is a heated zone. So as soon as that 0.1 microliter goes into the inlet, the temperature there must vaporize it. And this introduction must be in a reproducible manner. Remember, we're talking about accuracy and precision. It must be done in such a reproducible manner so that if you inject the same sample 1,001 times, it must be done in the same manner. And that is why automatic samplers are gaining more advantage over and above manual sampler, because if you're using manual sampler, different operators will introduce them in different ways. Even the same operator can introduce, the day you are very angry or tired, you just inject it anyhow. The day you are excited, the day you are anxious, so you won't be able to have reproducibility in your injection. But the auto sampler is the same. Given that the conditions are the same, your auto sampler will inject the same thing, the same manner over and over and over again. And one thing is that if you don't introduce your sample in a reproducible manner, it's going to affect your retention time. Remember, I told you in the last class that for the same analyte, the retention time must be the same each time you are injecting your sample. But if the injection is not done in a reproducible manner, what will happen will be the retention time would also not be reproducible, and you don't want that to happen, because your retention time is like a fingerprint for your sample. So how do we introduce sample? They are usually introduced using an hypodermic syringe through a self-sealing rubber septum. So inside the inlet, there is a rubber septum that your syringe will pierce. So your syringe will pierce through that. And once your syringe pierces pierces through it, you'll be able to introduce it directly. So there's a rubber septum. I remember going to take injection in the hospital, you have this injection where you want to inject, make a pull out or draw out a drug from a vial. There's a rubber septum at the tip that your needle can pierce through. So the same way your syringe will pass through the rubber septum into the inlet chamber, and there'll be a flash evaporation, and your sample will go into your GC. So solid sample cannot be introduced. It must be in liquid form. So your solid sample must be dissolved in volatile liquids, or or any other form of solvent, and it is introduced. You can also introduce gas, but the gas samples have their own special devices for introducing them. But the most common way of introducing sample to the GC is your sample extract, which is extracted into an organic solvent. You can't extract inside water. You can't extract inside acid, because of course your acid will contain water, and remember, water is an enemy of your GC. So the only way you can extract your sample is into an organic solvent. And sometimes, if you know that the organic solvent, there is water in it, you may have to pass your sample through anhydrous sodium sulfate, so that the water content in your sample will be removed, and you are sure that it's only organic solvent you are introducing into the GC, so that you don't damage your column. So samples are injected onto the column as a plug, and of a suitable size, like I said, from about 0.1, and depending on some columns can take up to 20 microliters. So, and the injector should provide consistent and reproducible injections. You must just have your injection in a reproducible manner, because you don't want your retention time to keep on changing. Today, your sample, this analyte comes out at 2.5 minutes. Tomorrow it comes out at 2.7 minutes. Next week is 1.7 minutes. No, your sample must be injected so that in a reproducible manner, so that your retention time will also be reproducible. And then the micro syringe is used to load the sample onto the column. So the syringe that must be used is a micro syringe, not a big one. And the syringe should be clean. So you don't, and after each injection, your syringe must be cleaned, because you don't want there to be a carryover from one sample. Unless you are working with sample, maybe 10 different extracts. If you don't clean your syringe, and you have the same syringe you are going to use, you have to clean it very well, so that there won't be any residual analytes of your previous sample that the syringe had injected. Your syringe also should be gas tight, so there won't be any vaporization of your sample that is going to inject. Then the syringe is injected into the injector through a rubber septum. The rubber septum has like a self-sealing closure. Once you withdraw your syringe, immediately the rubber septum closes. But you know that if you keep on piercing your rubber septum over and above the same, and if you're piercing the same spot, a time will come that the piercing would increase. So that is why your septum should be replaced after several injections, because you don't want that particular place not to be gas tight. If there's an opening in the septum, as you are withdrawing your syringe, some of your analytes or your sample would also get withdrawn, and you don't want to lose your sample. So the septum is not a permanent feature. A septum is very cheap. Maybe one is about maybe 1,000 naira. You can always replace by maybe after every 50 injections or 50 to 100 injections, you replace your septum. Then your auto sampler can be used, like I said before, and you must use a suitable solvent to enhance your separation. So the septum type injectors are the most common type, and the injectors are also composed of a glass tube. So there's a glass tube in your injector, and that is where the vaporization of the sample will take place. So the sample is introduced into the injector through the rubber septum. And remember that your carrier gas is already flowing. So as the vaporized sample gets into the flow of the carrier gas will flow through the injector and will carry the vaporized solute. And the temperature of the injector should be adjusted so that the solute will be vaporized and it goes into the column. So if the feature of the injector is not high enough, there will be what we call band broadening. If the temperature is high, is very high. So this is the schematic of the injector. You can see your syringe. The orange portion there is the septum that is going to pierce to make this place gas tight. Your carrier gas is flowing. This is the entry of the carrier gas. The carrier gas is flowing through here. So your sample is injected, and this is your glass tube, which is called the vaporization chamber, and is also heated. So this is the column. Your column too will, part of your column will go into the chamber, and so as soon as you inject, the carrier gas is flowing. The sample gets injected into the carrier gas, and it goes into the column, and that is how you have your sample in your that goes into the column. So these are the different types of epidemic syringes. The micro syringe, very small. Some syringes are just 10 microliters. So if you doing manual and it's calibrated, so you can pick the volume you want manually, and you must be reproducible. Not that today you pick 0.1, the next injection you pick 0.4, another you pick. So that is why your auto sampler, you would have set it in the machine, pick 0.1 microliter, and your machine, like a robot, will just go to the sample, pick it, and you'd have set it also on the computer that after injecting, there will be solvent that is the auto sampler by itself will wash it. After every injection, it will wash, ready for the next injection. So this is the septum. You can see the needle piercing through the septum, and this is the syringe now. So it is rubber, and after several piercings, you can change your septum. So this is how it is. So this is the entry point of the injector. Your septum is here. So these are different types of septum, and the choice of your septum will be determined by the temperature. Some of them can withstand very high temperature. So you can see this septum now, there is a hole there. After several piercings, there'll be a hole. And when you don't have to wait until this point, because if the hole is too large, your sample will be, as soon as you are withdrawing your syringe, if there's a hole here, some of your vapor will come out, and you will not have the quantitative volume of your analytes or your sample into the injector. So as soon as you have done several injections, always replace your rubber septum. The rubber septum sits here. So there's the metal, everything. This is the injector, but it can be opened up, and you see now that your column will come from underneath here, and it will go in here. And so your septum comes here. So when you inject from this place, it passes through the hole here, There's a hole here, your injector, your septum sits here, and you inject your sample. So the mode of injection, for optimum column efficiency, you don't want your column to be overloaded with sample. So your sample size must not be too large, and your sample should be introduced on that column as a plug of vapor. Slow injection of large samples. So if you inject slowly, there'll be band broadening. Remember when we're talking about band broadening, you don't want your chromatogram to be like this. This is band broadening. You don't want this to happen in your chromatogram. You don't want this type of sample. So you want a chromatogram such that when you inject your sample, sorry, when you inject your sample, let me re-annotate it. So when you inject your sample, two things. You want your chromatogram to be something like this. So if you the one in brown shows if you use a very too large a volume, you will see that there will be band broadening, because too much of analytes, they will arrive at different times, and your sample would now arrive at the detector different ways. In addition to your eddy diffusion and also your mass transfer and all that, you now have your band shaped chromatogram. When you put very little quantity, you have a very good peak. So the most common injection method is where a micro syringe is used. We said before, it will pass through a rubber septum into a flash vaporizer at the head of the column. And the temperature of the sample pot where your injector is should usually be about 50 degrees higher than the boiling point of the least volatile component of the sample. So it must have a reasonable temperature higher than the least volatile component, so that you don't want there to be condensation. If that temperature in the injection pot is cold, the least volatile components will not become vaporized. They will just sit there and they will never enter the column, talk less getting to the detector. So we have different types of column. We have the capillary column and we have the packed column. The capillary column usually need very less sample. Then for capillary column, we can use what we call split injection or splitless injection. So there are two types of injection, split injection and splitless injection. So let's look at the two of them after one another. The split injection is usually useful when your sample is very concentrated. You know, when your sample is very concentrated, you are overloading the column, and we're not going to get a good chromatogram. So what we do is that a fraction of the sample is split before the sample gets into the column. So this is the entrance of this is your septum where your sample comes in. Your carrier gas is coming via this way, and there will be an outlet here, which is called the purge. So this is the purge of the extra, the vapor that comes out. So this is your liner. This that goes in is your column, the head of your column that goes into the injector. So as soon as the sample comes in, there will be vaporization here because it's heated. And if you now set a split ratio, you can set a split ratio of 100:1, meaning that one part of your sample that had been injected is what goes in here. The other ratio will be split, it will exit the column, the instrument, and it will go out out of the machine without going to the column. The reason why is that is because you are introducing very low volume of sample, 0.2, 0.1 microliter. How do you find 100 part of it? So when the carrier gas mixes with this vapor, that is where the split will take place, and the carrier gas and the vapor will carry a large chunk of it, and only a small fraction goes in there. And this is used when you have very high concentration of your analytes, not trace concentration. We are working at parts per billion level, parts per million level. You may not need to split, but if the concentration is very high, you have to split so that you have a very good shape of the peak and your peak will not be fronting. Then we have the splitless injection. The splitless injection, in there, everything is controlled by your computer. In that case, there will be a valve here that will shut this place, and everything that goes in there quantitatively goes into the column and they are separated. So in splitless injection, all of your sample is injected, directed into the column, and it is used for trace analysis. If the concentration is very, very, very low, you want everything into your column. So it's just an explanation of that. So when you are doing split mode, in the split mode, you close the valve, and in the split mode, the valve is open, and in the splitless mode, the valve is closed. So when it's splitless, you close this valve, and when it is split, you open. So this is your carrier gas, and the green arrows are your gas, your mobile phase. Your sample molecules is the triangle. Then the solvent there is the black. So everything gets mixed here. You form a ratio and you elute it. Someone is asking that there is no audio. I hope you can all hear me. Can you all hear me?
Yes, ma'am.
Okay, so that person is having an issue, not if the rest of the class is that person should, as has been advised, should log out and log in again. So your sample here now, when you open these vents, a ratio of it will be vented out, and only a portion that is allowed will go into the column. So and there's so this is your carrier gas flowing mixed with the sample molecule and the solvent that is carrying the sample, and it goes into the column. Now the column, which is the heart of the chromatography, where your separation takes place. The column, like I said before, sits in the oven. So this is the heart of the technique. And we have two types of columns. We have the packed column and we have the open tubular column. Packed column and open tubular column. So we have the packed and the open tubular column. The most common one that we use in chromatography is the open tubular column, which is also called the capillary column. So when you hear capillary GC, it's talking about the type of column that we use. So the packed columns were the ones, when the technique of gas chromatography started, it started with the use of packed column. But over the years, there have been a lot of advantages and disadvantages of packed column. So we now have what we call the open tubular column, which are the best, they are the better choices, and they are more robust, more applicable for GC analysis. So the packed column, as we said, they have the packed column are relatively short, less than 2 meters. That's for packed columns. They're usually very short, less than 2 meters. While your open tubular columns or capillary column can be as long as 30 to 100 meters. So those are the differences between a packed column and a capillary column. Who is this writing jargon on the slide? Laja, what is your name? So those are the differences between packed column. That is not just, the difference is not just with the difference is not just with the length. There are lots of other features that makes the packed column different from the capillary column. The packed columns are usually made of stainless steel or glass, while the open tubular columns are made of the silica, fused silica. So that's another difference between them. Then the temperature of the column is adjusted such that it is close to the average boiling point of the sample mixture. And the only way you can adjust the temperature of the column is by adjusting the temperature of the oven. So the oven temperature, automatically the column will take the temperature that is set for the oven. So in setting the temperature of the column, you just adjust the temperature of the oven. And whatever the temperature of the oven that is set, the column will take that temperature. Temperature programming. So because our analytes are different, remember chromatography is about separation. Different analytes have different temperatures, have different boiling points, different volatilities. So how do we do this? And we can't just put one temperature. If you set one temperature, the temperature is lower than the boiling point of the least volatile components, they will not become volatilized. So how do we do this? We do what we call temperature programming, which is used to achieve better separation. And so like I will look at that in details later on. So like I said before, the temperature of the column is assumed to be the temperature of the oven. So you won't see, if you are operating, you won't say this is the temperature of the column oven. You usually say the temperature of the column, because it's the same temperature you set for the oven that the temperature would assume. And also, you want the temperature to be stable, because if the temperature is not stable, your results will not be reproducible. Today, if the column is not in an oven, the day the temperature is very sunny, like the atmospheric temperature changes day in, day out. So you can't rely on the atmospheric temperature. And that is why the oven will give us a stable temperature that will be reproducible, that once you set it on the computer, the temperature will be the same. So these are the, you can see these are how the columns are. So these are the columns, they sit in the thermostatically controlled oven or environment, which changes, the temperature change should not be more than plus or minus 0.5 degrees. Means that if you set it at 100, the highest it can go is 100.5, and the least it can go is on 99.5. So that is the range within there could be adjustments, because temperature is very important in GC. So the temperature is set. So a different analytes will come out at their own different temperatures. So these are the column. You can see the column is always having two ends. One end goes into the injector, the other end goes into the detector. This end goes into the injector, detector. When you buy it, there'll be a label on the column. Every column comes with this label, and this one is a very thin one. You can see these ones are thicker and fatter, and while this one is very thin. Columns are known by their internal diameters. So the diameter of this is very, very thin, and it is wound severally. And on this place, there will be the maximum temperature your column can be. If your column goes above the temperature set by the manufacturer, several things can happen. The stationary phase that is inside the column can wear out when the temperature is very high. The stationary phase can degrade, and once the stationary phase degrades, you just have an empty container. This is just a casing. What is actually doing the separation is the stationary phase inside the column. And if your column is degraded, all the stationary phase inside had been removed because of very high temperature, nothing will be carrying out the separation of your analytes. So for precise work, the column temperature must be controlled. You have to control your column temperature within tenths of a degree. And the optimum column temperature is usually dependent on the boiling point of the sample. A temperature that is slightly above the average boiling point of the sample results in an elution time of 2 to 30 minutes. Depending on the length of the column, the length of the column would also have to play a role in the elution time. If you are using a 30-meter column, the elution time will be different once your column changes to 100 meters, because your analytes will travel a longer journey in a 100-meter column than a 30-meter column. Minimal temperatures will give good resolution, but it will increase the elution time. The temperature is very low, the analytes will take a longer time before they elute. If it is too high, all of them may attempt to come out at the same time. So you have a very poor separation. So you have to optimize your temperature. So if your sample now has a wide boiling range, you have some that maybe they will boil at 120, 150, 250, 300, different analytes having different temperature ranges. What we do in that case, we do what we call temperature programming. And temperature programming would have to do that different components of your sample will elute at their own optimal temperature. So that is what we call temperature programming. So now let's look in depth at what this temperature programming is all about. Remember, we say that temperature is key. Temperature is very important in gas chromatography. And so for this reason, there are two ways the GC works with temperature. The first one is isothermal temperature. Isothermal means that from the beginning of your analysis, when you inject your sample, till the last component elutes from your chromatogram, you are using just one temperature. You set your oven at, say, 250 degrees from beginning till the end, no change. And this is useful when your components of the mixture, they all have maybe you have very few components, maybe two components, and they have similarities in their temperature. And their temperature, their boiling points are close to each other. So you just put one temperature, and since they have similar temperature, what can now separate them might be maybe their dipole-dipole interaction or van der Waals interaction of your analyte with the stationary phase, but their temperature is similar. And it's not usually a multi-component sample, maybe just two analytes you want to separate, or 3 or 4. But we are separating like 16, 30. Definitely they will not have similar boiling points. And in that case, that is what will inform us to use what we call temperature programming. So know the difference between the two. Isothermal separation is when you have closely similar boiling points and your sample contains very few components or analytes. But when you have multi-components with different sizes or different range of boiling points, you can't use the same temperature from beginning to the end. What will happen is either the volatile ones will not get to the detector, they will just sit in the column. Let's say, for example, your temperature of your oven is 180 degrees, and there's an analyte there that would boil at 250 degrees. That means that even if you put that sample there for a whole day, it will stay in that column. It will not leave the column, and it will not get detected, and it will not be separated. So that is the reason why temperature program, as the temperature is increasing, different components will be boiling off and getting out of the column at their own different retention times. So when you have a multi-component mixture, you have to use temperature programming. So the temperature program analysis is preferred for samples that have wide range of boiling points and they have different sizes. So what temperature programming does is that it ensures complete and efficient separation, as well as the efficient is complete, because if your analytes are held back in the column, your separation is not complete. You have injected 20 components, only 15 were detected. The remaining 5 are sitting in the column because of very low temperature. That separation is not complete. So temperature programming ensures complete separation, efficient. Even when temperatures are programmed, your peak will be very sharp. There won't be band broadening because each analyte will come out at their own comfortable temperature. They are not being forced to come out or being pulled out. And if you are forcing them to come out, that's when your peak will be tailing or dragging or fronting. Also, the optimum column temperature will be dependent on the boiling points of your sample. So you must know the chemistry of your sample. When you know the chemistry of the sample, you'll be able to know which one is coming out at which temperature. So now comparing the two, isothermal operation and temperature programming. In isothermal operation, the column runs at a constant temperature throughout the entire separation process. But in temperature programming, the column temperature rises continuously at a predominant rate. Also, in isothermal operation, the temperature at the midpoint of the boiling point range is used as the isothermal temperature. Let's say I have three components. One boils at 100, the other one 110, the other one 120. I will use the one that is middle, so that the one at 120 will still manage at a later time to come out. So there'll be a compromise. If you have a close temperature of the boiling point of your analyte. But in temperature programming, the lower temperature, you start with the lowest temperature, means that the very volatile ones that will boil at lower temperature will elute fast. Then the less volatile one that will elute at higher temperature will come out as the temperature increases. There are disadvantages in isothermal operation because whenever you are having heavy compounds with higher molecular weights and higher boiling points, they will not come out, like I said before. And the disadvantage of isothermal operation is that there'll be poor resolution of the lighter components at higher temperature. So let's say the temperature is set at 100. Those that will boil at 70, 80, they will just come out in a hurry, and they won't be good results. All of them, maybe 70, analytes of 70, 80, 90, 95 degrees, they might even come out together at once because the temperature is 100. Then sometimes for compounds that will come out later, there'll be broad peaks. Then there'll be carryover of the components that, maybe the components that are sitting in the oven, once their temperature is not attained, they will stay there. So maybe next week, you now inject another sample and you now change the temperature. Those ones that were there before, they will now come out. And they may not be what you are looking for in your sample that you have just injected. So there'll be carryover, and we call them ghost peaks. Ghost peaks are what are not part of what you have injected, but they've been sitting in the column because waiting for that temperature that will bring them out. So it might be the following week or the following month or the next temperature programming that suits them. That is when they will come out. And also the run time is long. As an analytical chemist, you don't want to spend a whole day analyzing just one sample. So you want to optimize that. You want to have good separation within a reasonable length of time. Then also lower sample throughput. You won't be able to do so much when you are doing isothermal operation. But temperature programming has a lot of advantages. The lighter compounds will be high, there'll be resolution of the lighter compounds because the temperature will be optimum for them to come out. Your peaks will be sharp. The length of time of running will be shorter. There won't be any carryover. All of them will come out. Then there will be higher sample throughput because you will analyze your sample quick. Then it can be, the application range can be extended, so you can modify different components to come out at different times. So now let's see these two chromatograms on the board. The first one at the top here, we want to separate alkanes. We have alkanes up to C21. In the top chromatogram on the left, it was isothermal temperature. That means that from the beginning of your injection till the end, the temperature was the same at 150 degrees. See what happened when you inject all these ones. See the way they came out. Almost all of them came out at the same time because probably their temperature boiling point is below 150. So as soon as they get in, they all leave the column. So you see them co-eluting. You can't say there's a separation here. And even the ones that are separated, see the way the peaks are. Broad, not nicely shaped, and 95 minutes, as at 95 minutes, only C15 was able to come out at this temperature at 95 minutes. Now let's look at this temperature programming. We are starting initially at 50 degrees, and every minute the temperature is increasing at 8 degrees. So this is called temperature programming. There'll be a start temperature and there'll be a ramp at every minute. Sometimes that by the start, you have 50 degrees. Then after by 60 minutes, it becomes 58. By this second minute becomes 64, I'll be 66, and temperature will be increasing like that until 250 degrees. See what happened here. By 36 minutes, carbon 21 are eluted. See here at 95 minutes, we're still on 15, and nothing else may come out again because the higher boiling points, alkanes, will never get evaporated at this temperature. So what happens? They sit in the column until maybe a day comes and you have to change the temperature, and they will now come out, and they may now elute in a chromatogram of a sample that is not theirs. So that is why temperature program, you can see the shape of the peaks nicely separated. And within 36 minutes, C21 are eluted. So the lower chromatogram, the temperature is programmed to increase with time, and the temperature and the compounds with higher boiling points will elute faster and show sharper peaks. So the optimum column temperature is dependent upon the boiling point of the sample components. See another one here, another example illustration. See these components now. In 30 minutes, see the shape of this peak. See how far it is on the right-hand side, the chromatogram on the right-hand side. See the peak of the fifth chromatogram. You see the weight was broadened. The first two, three, for the 1 and 2, see how it is. This is isothermal at a very low temperature. Now, let's say the temperature is too low. That is why this one is not coming out well. Increase the temperature to 145, isothermal. See what happened. The first 6 components came out, but other components that had higher temperature managed to come out 6, 7, 8. But because this temperature was not suitable for them, see how the shape of the peak is. But this one are now programmed to start at 30 degrees and to increase gradually to 180. You can see within that same 30 minutes, 9 peaks came out, and they are all nicely separated. So this is the advantage of temperature programming. So this is how temperature programming starts. A temperature program consists of a series of isothermal and temperature rise steps. So we have 3 variables that play initial role in temperature programming. There'll be an initial, look at the graph here on the right-hand side. There's an initial temperature. So I can say start at, so this axis is your temperature and this is time. I could say start at 50 degrees and be isothermal for 2 minutes or 5 minutes. So for 50 degrees, I would have an isothermal temperature. I will now tell you that it should increase at maybe 10 degrees per minute until 200 degrees. So I would now say increase at 10 degrees per minute from that 50 until 200. So we'll now be increasing, and this is called a ramp. Then at that 200, I can say, okay, you remain isothermal for 5 minutes or 10 minutes, will be isothermal. Then maybe this is the final time. And after that, it will cool down again and waiting to inject another sample. So it's a cycle, because I'm not just analyzing one sample. So this cycle now, this program will continue to be replicated. So it will start, there'll be an isothermal holding time, there'll be a ramp, increase in temperature. You can ramp it 2 or 3 times. So you could have your temperature programming, you could have it a start, isothermal, ramp at a certain temperature, get to a certain temperature. You can tell it to also be isothermal again, ramp it again. Sorry. So you could start, let me start it. You have an initial temperature. You have an initial temperature here. Can tell you to increase at a certain rate, hold it isothermally, increase again, hold it isothermally, increase again before it goes back. So it depends, you are the one that will know which one is optimal. And the way chromatography works is that if I do this, I'll look at my chromatogram. If between this retention time, if there's a retention time here that my samples are not well separated, I can change the temperature programming. So you can always alter and modify your temperature programming. You want to note that your samples are not well separated. Can you still see my slide? No.
No, ma.
No, ma.
All right. I clicked on something and
No
it left.
more.
Okay, so let me go back. Can you see it now?
Yes.
Yes,
Yes,
ma'am.
ma.
Okay,
Yes,
Yes, ma'am.
ma.
Yes,
okay, yes.
yes, ma'am.
No,
So
ma.
you can't see my slides.
I don't see anything.
I can
We can
see
see
it.
it, ma.
All
We
right,
can see it, ma'am.
all right, thank you. So the
We
initial temperature should be such that the most volatile components are adequately separated. So this is the initial temperature. So this temperature is generally well below the boiling point of the lowest boiling components. Then you now have the final temperature, which will accommodate. So in this, like the previous chromatogram that we have. So at this stage now, your temperature, these ones now, their own temperature will be very high. At this end, the temperature will be increasing gradually as the boiling points of the components that were loose. So remember that in your temperature, there is this x-axis is your time. It also corresponds to your retention time. So once you do your chromatogram, for example, here, I see now that at this particular temperature, between 10 and 20, this is what is happening. I will now go to that temperature programming and alter the temperature there so that it will accommodate the temperature of the analytes that will elute at that time. And once you get to the final temperature, when your last component comes out, the oven automatically will be set that it will cool down to the lowest temperature again. And once the instrument will not be ready until the oven gets to this temperature, especially when you are doing auto sampling, the auto sampler will not pick another sample until the temperature cools down to the starting temperature and another sample is injected. So the oven, we've said that it's controlled. We've talked about the oven as it is. So now the types of column, the column types. We have different types of column. Like I've said before, we have the packed column and we have the open tubular column, or what we call the capillary column. And there are three things that define your column: the length of the column, the thickness of the stationary phase in the column, and the inner diameter, we call the ID of the column. So when you buy a column or you see a column, unfortunately, this is the virtual class. I would have taken you to the lab where you see the column as it is. You will see the length of the column. It will let you know the length. Then the stationary phase. Remember, we said that the stationary phase is inside the column, and the stationary phase is lined inside the wall. So like in this place now, this gray part is the outer wall of the column. The blue component is the inner side of the column, and that is where your stationary phase is embedded. So, and the thickness of the stationary phase would also be determined by what the column has the capacity to do. And the thickness can be 0.1 to 0.5 micrometers. And then the inner diameter of the column is also defined. It ranges from 0.1 to 0.53. And that's why you are doing chromatography. You have to state all these parameters in your methodology, because if the thickness of your stationary phase changes, the way the separation will be achieved will be different. So if I use 0.1 thickness, you use 0.2 thickness stationary phase, we won't achieve the same separation. If my own stationary, my column is 30 meters, you are using 60 meters, our retention times will be different. So that is what you need to know. And these columns are fitted into a thermostatically controlled oven. And you can see that they form coil. You can imagine having 100 meters, and I've told you to visualize if you're running on a track. If you're running on a track, you can imagine how 100 meters is. If it is not coiled, that means your GC you have to build an entire warehouse for your GC to put your column. That is why it has to be coiled. And that oven will control the temperature that if you set it at 100, if you will go above that, be plus or minus 0.5. That is what is meant by thermostatically controlled oven, and it won't go beyond that, and it will maintain that temperature for the period of time. Then a capillary column is more efficient. Remember, we're talking about the efficiency, we're talking about number of theoretical plates. the higher the number of theoretical plates, the more efficient your column is. So columns that are longer, capillary columns are usually longer than packed columns, so they are more efficient and they separate better. Look at the picture of the capillary column. I am tired. I will soon end this class. I'm sure you are also tired too. We'll have our test at the end of the class. So those of you that are leaving, you won't get your question. So this is the packed column. The packed. Who is talking there? Who is saying, Ubaka? It's you that will talk over Sabi housewife. So you see a column here. This is a packed column. The circle inside, those are the stationary phase. So your packed column is like you are pouring something and you are filling the entire column. That is how the packed columns are. And I've told you before that they are usually made of stationary phase and they are shorter than the capillary column, between 1 and 4, about 5 centimeters, and their internal diameter is wider. Because the internal diameter is in millimeters. Meanwhile, 1 to 4 millimeters. No. Then the column is packed with finely divided particles. Remember, your column is just the house. What is doing the separation is, we said, is the stationary phase here. So they are usually fine, like your silica gel. You can visualize pouring silica gel into a column, or maybe your burettes. Pour silica gel in it. That is you have packed that column. That is a packed column. So, and their internal diameter is wider, about 100 to 300 micron. Remember, for the capillary one, they have smaller capillary diameter. So they are, and they are usually used for large scale separation. When do you want us to have another class? So let me stop here so I can easily upload this video. Can we meet later in the day? Hello? And there was silence in heaven. Can we meet later in the day? Yes?
Ma, we have CHM 435 class at 4 p.m.
At 4 p.m. And we can have our own by 7 p.m. That is the advantage. At least you are not, I'm not saying go home and bring the enter taxi and bus and come back. Let's have our own by 7 p.m. or 8 p.m. So we'll meet at 7 p.m. Thank you very much. And I think our test, the test will be we'll do a short quiz at 7 p.m. when we meet. And it will cover what we have done this morning.
Yeah.
Thank you. So see you by 7 p.m. Yes, I'm listening.
How do we get the video, the recording?
Were you not in class? Were you not writing anything down? You are watching Netflix, Abby. My class is Netflix. I'm not writing anything. Eh?
My most of us depend in lab and you can't be on campus by 7 p.m.
Who is asking? Did the Vice Chancellor say you should come to the
Most of us use
it's the lab consider us, please.
Consider which people?
would the recording be available?
No. Recording is not available.
Please help me now.
Recording is not available, and slide will not be available until the end of the class, the whole lecture. That's what I will share the slide.
Wow.
So see you by 7 p.m.
We have the class maybe on that day.
On Monday.
Man, please, can you make the class on Monday, ma, please?
So that we can read, the one we can digest the one we done today, because hey,
we can use your time, man.
Maybe in the morning too.
Okay, 9 o'clock on Monday.
Yes,
on Monday, we're also having a multiple choice.
I was trying to write during
Monday.
class.
I can't hear
We're
you.
giving you multiple choice.
Multiple
So
choice.
I was trying to
Singular choice.
They ask for multiple choice. Main class no
Who is
J.
saying multiple choice?
Wait.
I'm even the one giving you opportunity to be talking. We are meeting on Monday by Kelechi talk. You raise your hand.
Sorry, ma. I wanted to ask a question, ma, concerning isolated temperature, concerning isothermal.
Uh-huh.
Ma, I wanted to ask, please, how do we elude isothermal operation?
How do you elude isothermal?
Yes, isothermal.
Once your carrier gas is moving, once it's flowing, and if your separation takes place in the column, the carrier gas will carry it to the detector and it will be detected. Whether it is isothermal or temperature program, your mobile phase is flowing. Once the column separates it, it will deposit it at the mouth of the detector, and the detector will pick a signal.
Okay, ma.
I want to ask another question.
Yes.
There is this and the number of theoretical plates equals to the length over the height.
Yes.
Now the length I know is the length of the column, but the height is said to be the distance through which something traveled. But isn't that supposed to still approximately be equal to the length of the column, or is there any other type of
plate? Height equivalent to one theoretical plate. Let's say HECP. The height is equivalent to one theoretical plate. Remember the picture I showed where there was a partition in the column. Each of that is an equilibration step, and I said it's equivalent to, if you are doing liquid extraction and you are doing 3 extractions, 5 extractions. So each theoretical plate is an equilibration step, whether by partitioning or by partitioning or adsorption. So every step there, so each length is the entire length of the column is the length of the column. The H there is the height equivalent to a theoretical plate, not the length of the column.
Does that approximate the thickness of the stationary phase that is coated inside the column?
Remember, these things are theoretical. It's not what you can measure on your column. These are just the theories of the principle behind the separation. This is not what you now get your column and now get rule and start measuring it. They are all theoretical calculations. Okay. So we'll meet on Monday by 9 a.m.
Thank you.
So I'll send the link to you over the weekend.
we have test on Monday, ma.
So what has that got to do with me?
Ma, Monday is okay, ma. Monday is okay, ma.
Please,
Monday is okay,
ma.
Please.
Ma, Monday.
Ma, please, I want to
Monday
ask.
is okay, ma.
Hello, ma.
Yes.
Please, ma, we need.
You need what?
It's not okay. Oh. We haven't test on Monday.
Ma, Monday is okay.
If you're having a test, are you only doing 1 course per day? What's my business with having a test? You have a test, that is not, I'm not disturbing the test, and the test is not disturbing my lecture. So because you're in the comfort of your homes, you can be dictating to me to come and at your own, you should even want me to come to your house and give you the slide in your house. So no more talk. 9 o'clock on Monday, we'll continue the class, and we're starting with the quiz. So once you log in, the question will be online and you submit within 5 minutes. If you like, come in after 9 o'clock, you will not meet anything. By then, we would have continued the lectures. Have a nice day. Bye.
Thank you. Have a nice day, ma.